Hello everyone, and in honor of Interstellar's 10th anniversary, and it being re-released in theaters, and hopefully I will go see it. I just didn't get tickets to go see it this time around, but I'll probably see it with friends soon, hopefully. But today we are going to be doing some general relativity in honor of Interstellar, and specifically we're going to be solving for the Schwarzschild metric and do some black hole things. So, without further ado, let's get started with field equations. Woo! Okay. So the first thing we're going to do with our field equations is get them to the form where we can apply the assumption every element of our stress energy tensor is equal to 0, because we're assuming that we have some point mass in space and we want to find the curvature of space around said mass, right? So what we're going to do to be able to apply this, because we can apply this right now, right? But we end up having this not so nice term, so let's rewrite this equation and then apply this, shall we? So what we're going to do actually, takes me like multiple seconds to change colors when I'm not on one note. But what we're going to do is multiply both sides of the equation by g mu nu. And what this is going to do is allow us to effectively take the trace of this right here and do some things with this. So with this term right here, this first term, well, we have g mu nu times our Ricci tensor, and what this is just going to give us, we know it is literally just going to be capital R. It's going to be our Riemann curvature scalar. And then we're going to have minus 1/2 R, and then g mu nu, g mu nu. And I'm going to move this, I'll move that somewhere else. But this right here, we have g mu nu times g mu nu, but we know that these matrices are just going to be inverses of each other, and multiplying them together like this is just going to give us the trace. So what we have here is just going to be the dimension of g, which in this case is just going to be 4, because we're working in 4-dimensional space-time, 3-dimension space, 1-dimension time. And what does this equal? Well, this is going to equal some constant times g mu nu, and then times t mu nu. And this right here, like similar to this, it is just going to give us some constant, which we can just call capital T. So what does this give us in total? Well, what we have then is r minus this right here. Well, this is just 4, so we have 4 over 2, which is just 2r. So we have r minus 2r, which is just going to give us negative r, which equals this right here, kt, or kappa t, really. And given this, we can just solve for r. So moving this around, we see r is equal to minus kappa t. And we can substitute this into our original field equations. So doing this, what we have is then, well, we know that r is equal to minus k, or minus kappa t. So we have r mu nu is equal to, well, 1/2 r g mu nu, so we just plug this in, right? So now we have plus k, or kappa t, because we just set that in over 2, g mu nu. And then this is equal to just kappa t mu nu. But since we're operating under the assumption that there is no other mass present, we say that t mu nu is going to be equal to 0. Every component of it is just 0, which also means this capital T is going to be 0. Thus, that's 0, and that is 0, which leaves us with just this term being equal to 0. So we now just have our Ricci tensor. I'm just going to erase this. Our Ricci tensor, r mu nu, equaling 0. So now what we have to do is evaluate this equation right here. So given that we have our Ricci tensor equal to 0, we can just expand that out and now try to solve the field equations. So we have the expanded version of that, and I've also taken the liberty to include the definition of our Christoffel symbols right here, because, well, you see that we do need to calculate quite a few of them. So let's get calculating, but before we do, what we're going to need is our metric. And we're going to be assuming that our metric is going to be in the form, so g mu nu is going to be in the following form. We're going to have a right here of r, minus b of r, minus r squared, and then minus r squared sine squared theta. And this is going to be a diagonalized, this tensor is going to be diagonal. And you'll see a couple things from this. First off, it is spherically symmetric. So this right here is just going to be the same thing, or the same terms you would find in the metric tensor for just normal 3D space, but in spherical coordinates. And then we just have, the only two things that are altered are a and b right here. These two are going to be functions of r. So you'll notice a couple of things here that we will be using quite a bit. And the first one is that any off-diagonal components are immediately going to go to 0. So if you notice in this equation right here, we see that we have lots of g and then like b, c. If b does not equal c, and these right here, if these don't equal each other, then this term right here is just going to be 0. And immediately we can see that we have there's an implied sum over k, right? So we have g a k. But if a does not or if k does not equal a, that term is not going to contribute anything to the sum. So we can actually simplify this immediately by replacing all of our k's with just a's. So now we have GAA. This becomes an A, another A, and then another A. This is simplified quite a bit. Another thing is that this metric is static, so it's not changing over time. So if we differentiate this with respect to time, every component is going to be 0. If we differentiate this with respect to phi, it is also going to be 0, though it should be noted that the coordinates we're using, this is like the t column, this is r, this is theta, and this right here is phi. It should be noted. So without further ado, let's get calculating some components of our Christoffel symbols, shall we? So what I'm going to do is, since there are a lot of these and we do need to log them, I'm going to write the matrices up here, or express them using matrices. So we're going to have gamma, like x, y, or x0, y. Then we're going to have a matrix, and then we're going to have gamma 1, x, y, another matrix, and so on and so forth. And I'll add those in as we go. But one more thing before we start calculating Christoffel symbols. I'm only going to be computing the ones that are non-zero, as there are a whole lot of them, and only 13 are actually non-zero. So for the sake of time and brevity and my own sanity, we are only going to be calculating the ones that are non-zero. So let's get calculating our Christoffel symbols. We're going to start with gamma of 1, 0, 0 right here. And we see that we have 1/2. And then the inverse of our metric right here is just going to be 1 over each of the components, since it is completely diagonal. So what we have is GAA, A is 1. So we're just going to take 1 over our first component. So we have 1 over negative B. So negative and then B. And then here we have negative partial, well, A is just going to be 1, so our first coordinate, which is R, of GBC, but BC is just 0, so we just take this component right here, A. So this right here, you'll notice that these cancel, and we just have A prime over 2B. So putting that in, we have A prime over 2B. And then let's calculate our next one. So we have gamma of 0, 0, 1. And this right here is going to be something similar, only that A is equal to B in this case, so we just care about this right here. So inside our parentheses, we have partial R and then G0, 0, so that's going to be partial RA. But outside, we have 1/2 G0, 0, so that's just going to be 1 over 2A. And this right here is just A prime over 2A. So we have A prime over 2A. And this basically does it for this matrix right here. All the other components are just going to be 0. So writing all those in, there should be one more row of zeros, actually. I guess column. Yeah, okay, cool. An interesting thing about this matrix right here is the fact that it actually is just going to be diagonal as well. So we only have to worry about the following terms. Gamma 0, 1, 0. But you'll see here that because our Christoffel symbols, we can just interchange these two indices and we get the exact same thing. You'll notice that, well, or you'll remember that this right here is gamma 0, 0, 1. And the only two things that are different is that the bottom two indices are interchanged. So this right here is actually just going to be the exact same thing. So we can just kind of copy and paste quite conveniently, which is nice. Saves us a little bit of time and computation. And then next we have 1, 1. So all of these are going to be 1. Gamma 1, 1, 1. Well, if A equals B equals C, then this term right here, or this term, it doesn't matter, all these are going to be the same. So we have something plus something minus the same something, which is just going to give us the something. So we were just going to have partial, inside the parentheses at least, partial R, because, you know, these are all 1, G 1, 1, which is minus B. But then we also have 1/2 G 1, 1. So we have 1/2 G 1, 1, which is going to be minus B. So these cancel right here, and we end up having B prime over 2B, which is neat. And time for these next two. So now we have gamma of, let's see, 2, 1, 2. Here we have A equals C, so we only have to worry about this right here. We have B is equal to 1, so we have partial R. And then G 2, 2 is this component, that term right there, or that component, yeah. And 1 over, well, G 2, 2, but like upstairs is going to be R squared, or minus R squared as well, so it's minus 2R squared. And you'll see that these two terms, or the minuses cancel, and the derivative of this is 2R, so the 2's cancel. And the r's also cancel, so we have 2r over r squared, or 2r squared, and this just equals 1 over r. So here we have 1 over r. And for our final one, we have something actually really similar. Or well, the result's the same, but the way we get there is also very similar, just more stuff cancels. So here we have A equals C still. So we have 1/2, but we're just using this component now. So we have minus 2r squared sine squared theta. And then times partial, let's see, partial b, so partial r, of just negative r squared sine squared theta. And you'll see here that because this is a partial derivative, these are just going to cancel, and we get the same thing as before. So we have now 1 over r. Let's compute these terms, shall we? So we have gamma 2, but then let's see. So we have one row, so row 1, and then we have, well, 2 down here, so 2. So gamma 1, 2, 2. Let's compute that real fast. We have 1 over. We see that b, or well, sorry, this I guess. So 2, first term right here is just going to be a, or sorry, minus b actually. Sorry. Minus b, and then we also have b is equal to c. Since b equals c, we just have this right here, so minus partial r gbc, but bc right here are both 2, so we have minus r squared, so minus r squared. And here we just have, well, 2 of these negatives cancel, but we have 1 out front still, so it's really negative 2r over 2b, but these cancel, so we have just r over b, minus r over b. So this right here is just minus r over b. Next we have gamma, but then the indices, but just flipped, right? So we have 2 and then 1 now. So here we're going to have, well, a equals 2, so we have 1 over 2 and then times this right here, so minus r squared. And then we have partial a equals b, that means we use c, partial r of g22, so minus r squared. And you'll see here that these do cancel, or the minuses cancel, I should be more specific. These isn't, that's rather vague. But we have 2r over 2r squared, which is equal to just 1 over r. 1 over r. Next, we have gamma 3 to 3. And for this one right here, more or less the same. So 2, and then a is equal to 3. So now we have minus r squared sine squared theta. And then we have, inside of parentheses as well, a equals c. So we have this term right here, differentiating with respect to theta for the first time, of g33, which is this right here. So minus r squared sine squared theta. And you'll see here that the r squareds actually do just cancel. And what we're left with is 2 sine theta cos theta over sine squared theta, or 2 sine squared theta. 2's cancel, some sines cancel, and we end up with just cotangent. This right here is cot theta. And let's go on to our last set of Christoffel symbols. And here we have 4 more Christoffel symbols to compute, our last round of them. So now we have gamma. Let's see, 1, 3. So 1, 3, and this is already a 3. So this right here we have b is c. So we have 1/2. Well, we have a 1, so that's just going to be minus b. And then we have GBC minus partial, well, a is 1, so r, and then GBC, 3, 3, r squared sine theta, sine squared theta. Minuses cancel, and we're differentiating only with respect to r. So we just have 2r over 2b, and then times sine squared theta. So really it's r sine squared theta over b. So that right there is, I do apologize, there was an additional minus sign here. So we had 1 minus from this right here, then you have 1 more minus from that right there. So one of them would cancel, but we still have 1 more. That's minus. So we have r sine squared theta, r minus r sine squared theta over b. And then we have our next one. So we're just going to go down a row. So this is now a 2. So we have 1/2, and then times 2, this bad boy right here. So minus r squared. And then times partial b, or sorry, I can't start copying the formula, can I? B equals c. So we just have minus partial theta GBC, which is r squared minus r squared sine squared theta. Yeah, I did close the parentheses. Okay, so you see here that the r squareds do just cancel. So we're left with negative, and then the derivative of this. So we have, well, the 2's are going to cancel as well. So we just have minus sine theta cos theta, which I am going to be leaving as that. No fun angle identities today. So we have minus sine theta cos theta. And then now we have the other ones, right? So we're just going to reverse the indices here. We're going to have 3 and then 2. So we have 1/2, and then 3, 3. So 2 minus r squared sine squared theta, then times g, sorry, a equals b. So we just have this right here. So partial theta, and then g 3, 3. So minus r squared sine squared theta. So here you'll see that minus r squareds will just cancel, and we're just left with, well, the 2's will also cancel. So we're left with sine theta cos theta over sine squared theta, cancel, cancel, equals cotangent theta. This right here is cotangent theta. And then we're going to go on to this right here, so gamma 331. Gamma 331, we have, well, the same thing out front, so we have 2 minus r squared sine squared theta. And then we have, let's see, a equals b. A is b. So we have c, so partial r g33. Yes, g33, which is this right here, so minus r squared sine. Okay, and you'll see here that the sine squareds are just going to cancel, and what we're left with is just going to be, let's also cancel. So we have 2r over 2r squared equals 1 over r. 1 over r. So now that we have all of our Christoffel symbols, finally, we can go ahead and actually start calculating the components of this right here. So the first one we're going to consider is R00. Just for reference, this Ricci tensor under these circumstances is going to be diagonal, right? So any off-diagonal component is just going to be 0, just for reference. I'll leave that as an exercise for you to prove by yourself. But again, for the sake of brevity and my own sanity, we're going to be just calculating the diagonal components. So yeah. Here we have R00. So we have partial. I'm going to actually end up probably going past this, so I'll rewrite this at some point, I suppose. So we have partial mu, but mu and nu are just both 0. So partial t of Christoffel symbols, but again, I just erased it. That's funny. They're static. So this whole first term is just 0. We don't worry about it. This next one, though, you'll see that we have an implied sum, or we have our first encounter with a rho right here. It's an implied sum over both rho and lambda right here. So we have partial rho, and then this right here, so 0, 0. But let's take a look at this right here. We have 0 and then 0. So we have, it's this one. So we have this right here. We have our y is just 0, so we're limited to just this first column. And you'll see here that the only time you get a non-zero component is going to be when x is equal to 1. So in that case, we're just going to be differentiating a prime over 2b with respect to r. So that's exactly what it is. So you have partial r and then a prime over 2b. Okay, and then next we have these right here. So plus gamma and then 0 lambda rho, and then gamma 0 rho lambda. And these right here are actually quite interesting because the only time, and just look at this, it's mostly zeros, right? So the only time it's not going to be 0 is when lambda is equal to 1 and rho is 0, or the other way around. So what it's actually going to give us is this times this plus this times this, which because multiplication commutes, we can just write it as 2 times those two things. So 2 and then times a prime squared. I'll add parentheses. I'll add parentheses just to be clear. So a prime squared and then divided by 4ab. 4ab. Cool. And then now we have this right here. So we have minus gamma 0, or well, lambda 0, 0. But the only time that this right here is not 0 is when lambda's 1. So we can just throw that into here immediately. So we have a rho here, and just throw also that in there. So we have a prime over 2b. A prime over 2b. And then we just have to evaluate this sum right here. So we go over to this right here, and you'll see that it is literally just going to be the sum of our diagonal. So that's not awful. Maybe when we have to actually evaluate it later, but as of now, it's not awful. So a prime over 2a plus b prime over 2b plus 2 over r. And just simplifying stuff, just straight off the bat, you'll see here that we can actually factor out an a prime over 2b from here. So this right here, we have a prime over 2b. And what that leaves us with is just an a prime over a. And if we just make both these negative, actually, we can just throw this inside of here and see that we can have a this term minus, or yeah, and this term together. So a prime over 2a minus a prime over a, well, that's just going to be minus a prime over 2a. So what we can do to simplify this a bunch is just throw a negative sign in front of there and get rid of this term, which is nice. We've simplified this. It's a lot nicer now. Okay, now let's go on to R11. So R11. This right here, we're going to have, let's see, partial r now. So partial r of gamma rho 1 rho. And what this is right here, it's going to be the sum, or the derivative, partial derivative with respect to r of the sum of all of these right here. So what we have, you just throw that sum into there. So we have a prime over 2a plus b prime over 2b. And we will be evaluating some of these derivatives later, but I'm going to leave them as they are now because they will cancel to an extent. So now our next term, we have minus partial rho and then gamma rho 0, 0. Or sorry, 1, 1. I do apologize. 1, 1. But you see here, 1, 1. So we've got y equal 1, our columns equal 1. The only time that is not 0 is when x equals 1 as well. So we just have partial r and then this term right here. So b prime over 2b. And you'll see here immediately that these two terms do just cancel out, which is very nice. And then we go on to our next one. So plus gamma lambda rho 1 gamma rho 1 lambda. Okay, and we are back on one note because I was staying at school for a little bit too long and it got a bit late. But anyway, back to the math. I took the liberty of distributing a couple of things that we did have. So I distributed a couple things, and we can see here that we have a couple terms that actually can simplify quite a bit. So for example, these right here, these inner two terms, we see they have a prime squared b plus b a prime squared over 2. Well, that right there is just going to be negative 1/2 b a prime squared. So we can literally just erase this and then stick a negative sign there. And then similarly, in the numerator, we have a prime b prime, and then minus a prime over 2. So similarly, we can just erase this right here and stick a, but not the minus in front of there, and then just stick a 1/2 right there. And what we're going to do is just add these two equations together. And you'll see that a lot of the terms cancel, and that is the point. So you'll see that whenever we add these two equations together, these terms cancel, so we get 0. These terms right here that also correspond, we will get 0 there. We have this a prime b prime over 2, but then we'll see we also have this right here. So those two terms, even though I did write an a there, those two terms will actually cancel. So we get another 0 for those terms. So the only terms that are left, if we just kind of erase our zeros, logging that, are the minus 2ab a prime over r, and then minus 2b prime a squared over r. Those both equal 0. And we can just multiply both sides by negative r over 2, and we get the following. Plus. We can also just divide by a while we're at it, just to get it in this form right here. And we get a prime b plus ab prime. And that right there is literally just product rule. So what that is ab prime, ab all prime, equals 0. And integrating both sides, we find that ab is just going to equal a constant, and I'll call it constant capital K. This is different than the kappa at the beginning of the video, just for reference. But yes, we now know that AB is equal to some constant. But this is not enough information for us to solve for A and B on their own. We need additional information. So for that, we are going to, yes, I did copy all these. What we're going to do is calculate R to 2. And using that equation, we're going to solve for both A and B. So without further ado, let's get cracking. We have R to 2, right? So R to 2. So starting first off, we have the partial derivative with respect to theta. Partial theta of this right here. Well, gamma rho to rho. So looking at this right here, we'll see that literally the only term that isn't 0 along that diagonal is the last one. So 3, 3, and we just have to differentiate that right there. So we have the partial derivative with respect to theta of cotangent of theta. And then we have minus partial, or we just have our next term. I'm not gonna say all that again. But mu and nu are both 2, right? So if we take a look at this column right here, we see that the only time it's non-zero is when x is equal to 1. So as before, we have a partial derivative with respect to r of our term in here, which is minus r over b. But I'm going to cancel out the minus sign, so r over b. And then next we have, well, plus obviously, plus, and then we have gamma, lambda, 2, and then rho, and then same thing. And what that's going to be is the following. We're going to have, let's see, well, this term times this term, and then the other way around, right? So it's going to be minus 2 over b. And then we're going to have plus right here, this squared, so plus cotangent squared theta. And then for our final term, we are going to have, well, gamma, and then gamma lambda, mu nu, but mu and nu are both 2, right? So that means lambda has to be 1 again. So given that lambda must equal 1, we have, well, first off, the term in front is just going to be this one, so this minus r over b, but we can just make that a plus and put r over b here. And then we are going to have gamma rho 1 rho, and that right there is just going to be the usual, the sum of, whoa, that's not a straight line, the sum of this diagonal right here. So we're just going to add all those up. So we're going to have a prime over 2a. I did copy that down, right? Yay, I did. Okay. A prime over 2a plus b prime over 2b, and then plus 2 over r. And you'll see here that a lot of things may start to cancel. For example, you'll notice that this term right here, whenever we distribute it with this term right here, we end up getting a 2 over b, which will just cancel with this 2 over b right here. So these terms will just cancel. And there's also one more thing you will notice. This derivative with respect to theta of cotangent, well, that right there is just going to be minus cosecant squared. So minus cosecant squared theta. And whenever we add cotangent to this, or cotangent squared to this, well, it is just a Pythagorean identity that right there is just 1. So what we have, since those are 1, we have the following. 1, so 1, plus the partial derivative, or well, I'll write it just in terms of prime, so r over b and then prime, and then plus r over b, and then times a prime over, I'm just going to throw the 2 out just for the sake of brevity, and then b prime over b. And this right here is going to equal 0. Or I do apologize, this should be a -1. Whoopsies. But here's the thing. We already know A and B, sort of. We know that A times B is equal to some constant. So what we can do is plug in or substitute B's and turn this all into A's, and then just solve for A using this equation right here. So another way to write this equation actually would just be to say that this all right here equals 1. We can just do that. And we also know, I'll just write this on the side, AB equals some capital K. And from that, we also, those are both functions of R. just a reminder. So whenever we solve for a, we get a equals k over b. So what we have for this first term is going to be a r over k prime. So 1 over k, and then times this prime. And then what we have here is going to be plus r over 2k, and then we're going to have an a up top, times a prime over a. And then, well, what are we going to have here? Well, b prime is just going to be k over a. So we have, so plus k over a prime. But k over a prime is just going to be, well, minus a prime over a. And then we also have a b right here. So we have a k right here, a k, and then an a right here. Oh, sorry, this should be a squared. And then we see that these cancel. And what this leaves us with, there's an additional k up here from this b right here, so the k's also cancel. And we see that this whole term right here just goes to 0 immediately. So what we're left with is just this term on the left, which is just, well, ar prime equals, well, multiplying both sides by k equals k. So whenever we integrate this, because remember this is the derivative with respect to r, whenever we integrate this, we end up getting ar is equal to some kr and then plus s, where s is really just a constant, or a constant of integration. And whenever we divide both sides by r just to get a by itself, we get a is equal to, well, k and then plus s over r. And we also know that ab equals k, or in other words, b equals k over a. So we know from this that b is equal to k over a, so k and then over k plus s on r. And this right here, this is the solution. Almost. There is one more thing, and it's not from the equations we have here necessarily. It's just from physics in general. One thing we know about physics in general, or gravity, is that in the Newtonian limit, this first term right here, a, must approximately equal, or at least approach, 1 minus 2gm over c squared r. Just comparing terms here, we can actually just solve, kind of quote unquote, for k and s. So we can just say let k equal 1 and s equal this 2gm, or this minus 2gm over c squared. And this right here, or the absolute value of s, is actually called the Schwarzschild radius, which is quite interesting in and of itself. But this means that we can express a and b as the following. A is just going to be, well, that, where b is just going to be this 1 over 1 minus the Schwarzschild radius over r. So with all this in mind, we can actually just rewrite our metric entirely. We have g mu nu is equal to 1 minus the Schwarzschild radius over r, and then 1 minus the Schwarzschild radius over r, all to the negative 1. And then we have r, let's be minus, sorry. This should be minus r squared, and then minus r squared sine squared theta. And, well, we know that this is diagonal. That there, ladies and gentlemen, is the Schwarzschild metric. This has been, I think, one of the longest Physics Fridays. But I certainly had fun doing this, or really enjoyed the result, at least. Maybe I'm just justifying this long process to myself. But whatever the case, I hope you all enjoyed, and I will see you all in the next one. Happy December. Thank you for watching.